We're going to learn now about polarity in both bonds and molecules. A bond can be polar and a molecule can be polar. Well, you also can have nonpolar bonds and nonpolar molecules. And so what we're going to do is look at how this arises from differences in electronegativity values.
When we look at a bond, sometimes to determine bond polarity, we look at electronegativities. If the electronegativities are identical, for instance, two different carbons bound to each other, what you find is that their electronegativities are the same, and so we say it's a nonpolar bond. If I look at carbon and hydrogen, their electronegativities are different. Carbon is more electronegative than hydrogen. It's a pretty small difference between carbon and hydrogen, and usually when we're in a molecule that has carbon-hydrogen bonds, that carbon is tetrahedral and the symmetry of the molecule cancels out any electronegativity difference that there is. So for the most part, we just say carbon-hydrogen bonds are nonpolar. The electrons are considered to be shared equally in a nonpolar bond. However, if we go to something like a carbon-oxygen bond, carbon has an electronegativity of 2.5 and oxygen has an electronegativity of 3.5. That's considered to be a very large difference in electronegativity. That large difference in electronegativity causes the electrons to be drawn onto oxygen a significant amount. This gives oxygen a small negative charge, which we give as an indication a little del sign. That's a lowercase delta in Greek. We call that del, and we say del negative on the oxygen, and then a little bit of positive charge on the carbon, and we call that a del positive on the carbon. Another way of indicating this small shift in electrons is to use a vector as shown here, the little arrow with a plus on the end of it. The plus is always going to be on the atom with the less electronegativity, and the arrow pointing toward the atom with the greater electronegativity. What these dipoles show us is that the bond is polar, that one end of it has a small positive and the other has a small negative. This is very important to us. We'll see in the behavior of molecules and in their reactivity. So there's two ways to write a dipole, either del positive, del negative, or to write a vector. This indicates that the electrons are not shared equally. There's a small amount of charge on either atom, and remember, del negative on the atom with the greater electronegativity, or have the dipole point to the atom with the greater electronegativity. When looking at atoms that are in bonds, we can classify the bond based on their location in the periodic table. When atoms are very far apart on the periodic table, they are considered to have a big difference in electronegativity. When there's a huge difference in electronegativity, let's say potassium to sulfur, then we consider that to be an ionic bond. And I've already given you this rule that if you have a metal with a nonmetal, we consider it to be an ionic bond. If the atoms are close together in the periodic table, then we consider them to have a covalent bond. Now, if the electronegativities are very, very similar, let's say a difference of less than 0.5, carbon 2.1 and carbon 2.5 and hydrogen 2.1, well, the electronegativity difference is less than 0.5, so we say it's nonpolar. But if they are close together in the periodic table and they have a big difference in electronegativity, then we consider them to be polar covalent. Examples of polar covalent bonds are carbon-oxygen, carbon-nitrogen, oxygen-hydrogen, and nitrogen-hydrogen. Those are important bonds for you to remember, that they are covalent and very polar. If we look at entire molecules, we can also say that molecules are polar. There's two ways to classify polarity. We can say there are polar bonds, and there we look for a difference in electronegativity, or we can say the molecule as a whole is polar or nonpolar. If we're looking at an entire molecule, we can say that the molecule is either polar or nonpolar by looking at the polarity of the individual bonds and the overall shape of the molecule. If you have nonpolar bonds, well then we're going to say that the molecule is nonpolar. If we have polar bonds and the molecule has symmetry, the polarity of the bonds is canceled out by the symmetry of the molecule, and so then the molecule is nonpolar. But if we have a molecule that has polar bonds and it's asymmetrical, there's some asymmetry in there, then it will be a polar molecule. Well, let's simplify this and make it so it's a little bit easier for you to recognize. Nonpolar molecules usually have either very small dipoles in their bonds, for instance, carbon-hydrogen bonds, or they have no non-bonding pairs on the central atom, so the molecule is completely symmetrical and the individual bond dipoles cancel. So, if you see a molecule that is all carbon-hydrogen bonds, then we know it's nonpolar. If you see a molecule that is made up only of nitrogen, well, that must be nonpolar. But if you see a molecule that has no non-bonding pairs on the central atom and the individual bonds are very polar, it is still nonpolar, because no non-bonding pairs usually means the molecule is symmetrical. If we look at polar molecules, what we usually find is that there is a non-bonding pair on the central atom. Or sometimes it will be a non-bonding, one polar bond and the other non-polar bonds. This gives individual bond dipoles that do not cancel. Let's look at some examples. In the first molecule, this is formaldehyde. You can see the carbon-hydrogen bonds we consider to be nonpolar, but the carbon-oxygen is very polar, so this molecule as a whole is polar. If I look at the boron trifluoride, you can see there are no non-bonding pairs on the central atom. The molecule is symmetrical, and even though the boron-fluorine bond is very polar, the molecule has no non-bonding pairs on the central atom, and so it's a nonpolar molecule. If I look at ammonia, the third one, you can see there is a non-bonding pair on the central atom on the nitrogen, and we have polar bonds. Those polar bonds then make it so that the molecule as a whole is a polar molecule. But the key thing to notice is there is a non-bonding pair that's throwing the molecule into a little bit of asymmetry. So it's a polar molecule. If you look at the fourth example, you see you have two bonds to hydrogen. Those are considered to be nonpolar bonds, but the carbon-chlorine bonds are very polar. So we have two nonpolar bonds on one side of the molecule and two polar bonds on the other. This molecule is considered to be a polar molecule. Let's look at these molecules now using the principles that we've just looked at and try to identify, are these molecules polar or nonpolar? So is this molecule polar? The first thing we notice is that the phosphorus-bromine bond is polar. Phosphorus has an electronegativity of 2.1 and bromine 2.8. That would give the phosphorus a del positive and the bromine a del negative charge. However, even the most important thing to notice is that phosphorus has a non-bonding pair on that central atom. Because that non-bonding pair is there, it throws this molecule into a trigonal pyramidal shape, which is slightly asymmetrical. As a result, the molecule is polar. Is carbon disulfide polar? If we look at carbon disulfide, we will see that the bonds are nonpolar. Carbon and sulfur both have an electronegativity of 2.5. Likewise, there are no non-bonding pairs on the central atom. This makes the molecule symmetrical. So both the combination of nonpolar bonds and symmetry, the molecule is nonpolar. If I look at carbon tetrachloride, I can look and see that there are carbon-chlorine bonds in there, and they are polar. Carbon has a del positive charge and chlorine has a del negative charge. But the carbon atom has no non-bonding pairs on it. This means the molecule is symmetrical and will be nonpolar even though it has individual polar bonds. If I look at sulfur trioxide, I can see that the bonds are polar. Sulfur has an electronegativity of 2.5 and oxygen is 3.5. That's a significant difference in electronegativity, and they're very polar bonds. However, if I look at the sulfur atom, I can see that the central atom has no non-bonding pairs. When you have no non-bonding pairs on the central atom and the atoms attached are all the same, the molecule is symmetrical and it will be nonpolar. Don't forget to do problems. Do the in-text problems as you finish reading the chapter, and do the following end-of-chapter problems shown here that cover the material in Chapter 3, Part 2. Also find your online quizzes and worksheets that are posted for this chapter.